I'm trying to remember what I was doing in high school. It was not standing up at international conference presenting the work that I was doing in high school. So, with that, I'd like to introduce Farah Youssef. She's a high school student here residing in Dubai. She's the founder of space technology and education organization Astropoint, which works to spread the astronomical spirit of innovation through her magnitude of research experiences, including winning an Amazon Web Services grant for $60,000 worth of funding for her projects. She has incorporated feasibility and knows the importance of use for change. So with that,
hello everyone, thank you so much for being here today and giving me the opportunity to speak. My name is Farah Youssef. I'm a high school student here residing in Dubai, and I'm also the founder of Astropoint, a space organization dedicated to spreading awareness of the astronomical spirits of innovation. We work synchronously along the lines of both education and innovation with the emphasis of youth to highlight that space is not a construct but a tool. Space isn't just for the select niche of people who can count with our bare hands. It isn't only for the astrophysicists and astronauts, but a field for all people, and you showcase that today. So water, one of the most important ingredients of life, it is present in the moon's lunar surface. Previous missions like the Apollo program, Chang'e 1 and Chandrayaan mission have suggested that there is water present on the moon. Although it was believed that water can exist only on the far side of the moon, recent findings by NASA's SOFIA suggest that water can exist even on the sunlight side of the moon. Our paper proposes a 60-kilogram rover proven by preliminary studies at the Wiechert crater in search of water or water ice, extracting and lastly purifying it. This is significant since these ingredients can also be used for future human settlers, as well as develop economic prosperity and ensure commercial mining of water resources for electrolysis fuel cells. The main payload for this mission is the purification systems and the rocket fuel generator for the moon. The reason why this payload is chosen because these are 100% INSITU resources and can be drilled from the regolith. This is going to be working when the spectrometer and the hyperspectral images are going to be prospecting the lunar surface. Once the possible chances of water have been found, the drill is going to be extracting the water by heating the volatiles in the drill. We will then purify the water by using the hydrogen reduction and ammonia as a scrubber method, and these scrubbers to remove the excess gases from the vapor by purifying it with the help of the electrolysis system, which is called the MSEP. The next science payload is the mass spectrometer, which is going to be using a mass magnetic sector and a quadruple mass spectrometer to separate the ions and the compounds, which will then go to the detectors, which are both GC or a gas chromatograph. These are going to be working with the lasers that have melted the rocks for the gas to come out to be analyzed by the electron gun, and onto the filters of the RF iron beams and the magnets for separation, then onto the main detector, just as the working of the main mass spectrometer we're using. This type of spectrometer has never been used before since it's going to be a quadruple and a magnetic sector mass spectrometer, and these instruments and payloads are all technology demonstrations. So to reiterate the concept of INSITU resource utilization, it'll, as said by NASA, it'll enable the affordable establishment of extraterrestrial exploration and operations by minimizing the materials carried from the Earth. Slides. concept of operations for the last lunar rover to operate in are, first of all, the rover will find suitable landing spots using the TRN system, and the algorithm along with the cameras at the entry-descent landing craft. Once the landing spot is confirmed, the rover can then descend and go to the location desired. The rover will begin its mission at 84 degrees southeast of the Wiechert crater. Once it has developed its components and sends signals to the nearby communications on Earth for double systems checks, it will begin its journey in the search of water. Again, we reiterate the importance of using the TRN algorithm and navigation cameras to locate possible extraction points on the Wiechert crater for the icy bound or the water bound regolith, which we will explore in the other slide. The rover will be in contact with the Earth using the relay satellites on the Moon, like the LERO, and lunar flashlight, for example. This will be done with the S and X band antenna systems. We're using the LRO because the antenna sometimes cannot get a complete field view of the Earth, and hence the disruptions in the communication can cause the rover to not complete the vital information. Our speculated mission duration will be about 14 days, and the rover will start moving and testing out various systems like the robotic arm, mobility, and the sensors on the rover to verify everything is working perfectly. The sensors will once again confirm the areas of the water, like the instruments using the cameras and hyperspectral imagers and mass spectrometers. Once the rover is in the targeted area, the rover will collect and vaporize the samples, and the drills can start drilling and collecting samples for the extraction of volatiles. The process of drilling should be monitored using the sensors to measure its depths using LiDARs. So the drills will be using springs as well, and the cameras will monitor using differential algorithms to determine the depth of the drill. Due to the size of the drills, we won't have any sensors, we'll just be relying on the LiDAR technology. After the regolith is collected using an advanced purification mechanism, the unwanted material will be refined and removed from the regolith sample for the ease of water extraction using hydrogen reduction. This is going to be done when the heaters are inside the drill. Water will evaporate. Once the water has evaporated the volatiles, the water is vaporized at a certain pressure and temperature. The collected ice will be water, and then we will start to use electrolysis to use the hydrogen testing for the potential fuel for rockets and oxygen for astronauts. Then the drill will check and complete the collection process. After this, the arm will retract and go back into the rover. The process will repeat, and the purification and other discoveries can be done and made. This database is going to be the same, which is using a TRN, and the rover is going to be only operating on a lunar day. We will be putting the rover in hibernation when we hope that the rover will communicate with earthly warning. So more details on the drill that we are using is going to be 1.2 kilograms, and it's going to be making the arm only 4.2 kilograms in total. The robotic arm will work with the drill and is designed to extract the regolith and then used to heat and extract the lunar water. After this, the volatiles in the water will be allowed to pass through the cold finger, converting the water into the vapor into water states. The robotic arm will be long, and the cold finger is going to be connected to the truss itself for etch and dough, and is going to be purified for rocket fuel and for astronauts breathing. The drilling action pushes the cylindrical core inside, which has to be ejected out of the drill using vibrations and the rotation of the drill bit. The ejected core has to be brought back into the collection chamber using the robotic arm, and the proposed drill has been tested on Indiana limestone, having unconfined compressive strength of about 45 megapascals. The moon produces gamma rays, which are dependent mostly from the cosmic rays reflected. These rays are high energy, and they were tested from the Large Hadron Collider. As these cosmic rays are produced from the protons, atomic nuclei, and alpha particles, and other electrons, they are likely to be X-rays or gamma rays. On the moon, there is an annual explosion that is predominantly a larger range than Earth due to the lack of a magnetic field on the moon. These ranges from 380 MSV to 110 sieverts, or galactic cosmic rays. Cosmic rays are usually detected on Earth and are reflected from the sun. So we first decided to create a petrographic analysis of the regolith so we can determine the structural physics and the chemical composition behind the regolith. This also helps us identify the MSCP time period as well as to calculate what materials we're going to be extracting so that the rover is capable of operations. So the expected excavated regolith analysis will be high titanium phosphonated basalts, which show more density than the titanium ones, and the low titanium basalts have a prevalent amount of other substances that we can use for the scrubbers, like the aluminum oxide and the magnesium oxides. Fine lunar regoliths have fractions of glasses from the two repositories, which are non-crystalline material in basaltic rocks, and the glassy bonding material found in breccias. These impact glasses are approximately 3 to 5% and are produced from the melted exotic regolith. This shows that they are mixtures of different pre-existing rock types and not original, or else have been formed from the bombardment of heterogeneous substances on the exposure of other regoliths. We will also be purifying and testing the concentrations of the silicon, solar wind gases, calcium, and agglutinates, and we'll be performing strength tests on these materials through measuring the heat compression threshold of the porous lunar regolith. Porosity in terms of the volume of the regolith will be dependent on the void fraction of being pressured in the tubes. This will be allowed to be easier for the regolith to be transported to the mixture, and the thermal compression will be dependent on the compressive strength of the compressors. Another useful strategy is that we're going to be compressing the material on board, and for the thermal gradient to be decreased so that there's less temperatures that we're going to be using on a drastic scale. So here you can see a flow chart for the compression that we're going to be using. And we decided to locate the rover at the Wiechert crater because its surface ice has been mapped and it is part of the permanently shadowed regions. This will be our starting location using the TRN algorithms, and they will locate the exact extraction sites for us. And as per the LCOS experiment, there's about 1,545 grams of the water ice as per this experiment. Once the TRN extracts the location for the excavation of the regolith, we're going to be sending signals to the near lunar gateway and inform the regolith excavation trajectory. So to measure the material load penetrations and its effects, we will be testing using, as we said earlier, homogeneous batting water compression at 10.9 centimeter diameter using stainless steel rings, and then we're going to be cooling it down with liquid nitrogen. These temperatures will be measured constantly using a thermocouple. So what this caused was that it caused the intergranular ice of the regolith sample to be melted, and we could prevent failures of these using electrohydraulic servo-powered loops. They could also be used to test the saturation sample and the ice concentrations. And we're going to be using these experiments in the tubular reactors, where a given quantity of the regolith is placed inside with continuous heat flow using check valves. And we'll be using, for our plan, hypothetically, we suggested to use the PAR instrument company as it offers a two-phase flow and count current flows. So it adds a sort of catalytic bed to the experiment. And these tubular reactors are scaled down at only a size of 20 centimeters and a length of 35 centimeters. And then we're going to be using the ammonia as a scrubber and water polisher to contain and filter the water in the purification systems before regolith compression. Ammonia will also be stored in a purge line, which will include a shut-off valve, a filter, metering valve, and a backflow/double check valve. Another thing we're going to be purifying is the water from the ammonites, the titanium and basalts, and we'll be using the hydrogen reduction as proposed by Resolve, which will aim at finding iron oxides in the almonite or sometimes the glassy bonding material in the breccias. The reaction will involve iron dioxide in water, and we will be using a cold trap and Paragon Snephon-based ionomembrane water in the image for purification to measure contamination filtration percentage. So here is an example that we worked on of the MSCP. So as you can see there are the backflow valves and the electrohydraulic closed loop for the oxygen storage. And yes, so these were discussed earlier. So these are some of the onboard computers which my team and I worked on. We're beginning to be using the telemetry control experiments that are going to be programmed in C++ and C++ using Linux. The size of this PCB is only 63 by 58 by 10 centimeters in total, and we'll have a 12 interference, and it will be connected to the mission control on Earth, and also the LRO that we discussed earlier. And here are some of the other calculations that we use. So the solar irradiance, and the solar cell that we're only going to be requiring is about 1.2 meters squared, making this lunar rover again a small sort of power plantation. We're also going to be using junction multi-solar cells as opposed to with the lithium-ion battery, both of them together. In the rover deployed system, it's going to be only 120 centimeters by 50 centimeters when deployed, and we're going to be using an L-ion rechargeable battery as compared to other materials such as the solar power systems that reflect the rays. Yeah, so thank you for joining the mission to spread this powerful spirit of innovation, and I hope you enjoyed the idea.
we have time for a few questions.
Thank you. Yes, hello. This is Julio Morgan from ISA, the consultant. How do you do to arrive to the moon, which is the launcher that you will use, which are the spacecraft that you will use to go to the moon? This is one question. The other one is you will be in a very shallow place, so the solar panel will not work maybe. How long you will stay in this area alive during your mission? You compute how many days you need and how many energy you need to be there without the sun?
Yes, so the first question is assuming the lunar lander. So the lunar lander is going to be with the help of the lunar renaissance orbiter, and it's going to monitor the landing of the rover on the moon. For the second part is we're going to be 84 degrees south of the Wiechert crater. So south of that there is some sunlight, and we're also going to be connected to the SSPs around the moon, which reflect rays directly from the sun to our satellite, so we can actually catch the solar rays.
Thank you. Other questions? So I think you started that this is a concept, and then I saw towards the end that maybe there were some prototypes moved forward. So where are you in the mission lifetime for what you're trying to do?
So currently we're in the development stage, and we're recruiting other people to peer review our manuscripts. We're a team of 3, somebody in IIT Madras, my friend Shivam, who's also in another school, and we did this under the mentorship of a former Wiechert engineer. So what we're looking for now is that we're looking for sponsorships and potential opportunities to train our team to expand this project further, and so that we can connect with people and expand this idea of development.
Very good. Any other questions? Okay, let's thank our speaker again.
Thank you.